Welcome, everyone. Thank you for joining. Today, I'm excited to kick off this webinar, which is hosted by Keyfactor and NXP. And we are going to be talking about how important firmware signing is, especially when it comes to getting ready to be compliant with the Cyber Resilience Act. So I have two speakers here joining me, and they are experts in their space. I'm excited to introduce firstly Stella Orr, who is a product marketer at NXP. Stella, if you could just say hello and welcome to the crowd. I know we're going to hear a lot from you today. Welcome.
Hello, everyone. Hey.
We also have another colleague of mine, Ray Lilback, who is a senior director of IoT strategy at Keyfactor, and he will be joining us shortly. Ray, when you do get online, just please feel free to interrupt, say hello to the crowd. But looking forward to having you also join us. Hi, Ray. Can you hear us?
Yes. Can you hear me?
Amazing.
Oh,
Yeah. Welcome.
perfect.
So just kicking it off here, if you just want to say hello to the crowd, and then we'll jump right into the discussion. Okay. So for background, the clock is ticking. We're almost at the end of 2026, or sorry, 2025. 2026 is coming, which means one more year has passed, and developers and designers of connected products need to be ready to comply with the Cyber Resilience Act by December of 2027. There's dozens of requirements within this act that talk about how you need to have security, cybersecurity specifically for your product throughout that entire life cycle, from the initial boot up to all the way end of life and decommissioning. There's a lot of pieces that need to go into that. So OEMs have to design their products to support the secrets of today and the frameworks of today, but also be prepared for security in the future and have a flexible architecture to be able to handle that, including things such as post-quantum cryptography. So some of the things we're going to talk about today include secure boot, as well as what Keyfactor and NXP together with our software and hardware solutions are doing to help make it easier for OEMs to comply. So for the first piece of this discussion, I want to start with code signing. What is that? Why is it important for product security? And then what, as a piece of the CRA, we're following and people will need to comply with. And then lastly, how we're going to help overcome some pitfalls of outdated code signing processes and what we are seeing our customers implement today that is more modern. So first question. So Ray, I would love to have you talk through some of the basics of code signing. Why is it important? What is today's modern standard? And what are you seeing people implement?
Thanks, Ellen. So typically what we're seeing in the field is something that goes beyond what you've listed here, which is a checksum. Checksum's really there for making sure that a message didn't accidentally get changed during transmission. However, it's something that's easy to turn around and have to calculate and therefore to spoof. So someone can maliciously change the code, change the checksum, and it makes it look okay. What you need to do is establish a mechanism that allows you to, through an asymmetric key pair, create a hash of all of the software that you're putting on there, the code itself, the binary, and then take and encrypt that with a private key. The private key is the private portion of the asymmetric key pair. That can only be decrypted using the public key. So what ends up happening in this schema is that you create a private key. The private key is stored and really, really locked down so that no one can maliciously use it. You sign the hash with that. And then once the encrypted hash is sent over, you also send the public key to show, hey, look, I've got some degree of trust with this. And the public key can then be compared to a public key that's stored on the device. That public key becomes what we call a root of trust on the device. And if the public key matches and the decryption works correctly and you calculate the same hash, then you know that the code has not been modified since it was signed. So what that does is authenticate that the device code is the same as when it was signed. It provides integrity in the terms that it hasn't been tampered with, and you can trust the signature because you trust the public key. So that's the basics of what code signing is.
Thank you. So I'm just going to get back and see our faces here. We'll pull up a couple slides throughout this conversation, but want it really to be more of a dialogue. So I'll put out there the audience. If you do have a question, please go up into that question mark bubble up at the top, put in your question, then we'll get to it as we go through the topics. So Ray, next thing I want to talk to you more about is the challenges of code signing. So now that we know why we need code signing, what are some of the challenges that you see modern development teams facing when it comes to implementing this? And I know you talk to people weekly across a variety of industries, whether it's medical or automotive, but when it comes down to code signing, that is a process that goes across design teams, across companies, big and small. So just tell us a little bit more about challenges that you're seeing them, have.
So really, code signing is part of a process. And the big key is that the process itself is secure. Number one, you don't want to sign things with keys that are just sitting and living on laptops. And that's what we see a lot today, where the same key is pushed around to different developmental laptops as you do signatures. And then that signing, that process really isn't secure. You could have somebody steal the laptop. Therefore, they have access to that private key. Or worse, you could have some bad actor inside of the company create nefarious code, and this has happened before, and push it out with a good signature. So control of that private key and that signature operation is very important. In addition, regulations, automotive, medical, and the EU CRA all require auditability of when this signing and the signature took place. You need something that goes beyond just protecting the key in order to provide this type of auditability. So key protection falls into, hey, I could use something called the hardware security module. What is that? That is a secure enclave for private keys and private key operations. So not only does this hardware piece, which can sit in a data center that you own, or can be purchased from some of the cloud providers like AWS or Azure or Google. And that what that does is that is a trusted enclave. That enclave holds the private key. And more importantly, any operation that is the private key does is done within that secure enclave. Therefore, you have complete protection of the private key itself, so you can't see it. You don't get it exposed to the outside world ever. Everything happens inside of it. Now comes the next challenge. How do I make sure that only authorized signing applications or authorized signing operations happen? In order to do that, you need some means to control when that private key can be accessed. And that's where programs who are specialized in signing come into play. They allow you to take and do this exact same thing, turn on and turn off these keys only during signing operations. Good processes allow for managers to turn on and off the keys, and then the signature to take place by developers. That way you have more than one person involved in this entire operation. That also all is auditable in good security designed signing operation systems. So it's a process. It isn't just a piece of software. It isn't just an operation. It needs to be thought of holistically from a developmental standpoint and built in as part of your security operations.
Mm-hmm. Great points. And probably especially relevant when we have global development teams, right? You have people
100%.
working maybe around the clock, whether you're passing code from like India to Europe to the US, and developers all sort of working together. That's really important to have that process. Thank you, Ray, for that background.
Add on to that one other point. One of the other things that we see is the developmental keys. So you have a set of keys for development and you have a set of keys for production. Production needs to be very well controlled, but development can be different. And that's where having the ability to turn on and off production keys is more important than for development keys. That way you don't have to worry about getting a manager involved every time a developer needs to push new code to his device.
Great point. Thank you for adding that in. All right. Well, Stella, I would love to add your thoughts into the conversation. So we've mentioned the word trust a few times now. So I'm going to pull up a page here to add some context for you. But can you explain, what does trust mean to you? Why do we have to establish this? So please go ahead.
Yeah, so Ray explained very well about the fundamental and challenges of code signing. With the keys and certificate, we can protect software. We can prove the software is authentic. But now we may ask a question: how do we store our keys and certificates securely, and building the trust on an embedded system? So the first piece of the application code that we want to put up, we need to make sure it is authentic. So in embedded world, we relied on majorly two main features of a processor. The first one is a secure memory to store the signing key and certificate. And the second piece is we need an immutable boot-up code in ROM. Sometimes we just call it secure bootloader to verify the signature of an application code. So Ray mentioned about we can, during the production process, we can use the HSM to create the key pairs, the public key and private keys. And eventually, the private key will go into the processor to use for verifying the code that we want to put up. And the processor that containing all these features is the anchor of a system, of a secure system. We call it the root of trust of a system. This is because for the hardware design, for the hardware design, we design it to store the keys. We design the secure bootloader, which is immutable. It is not possible to change it later on with the design. So and also for the keys that for example, the OEM they provision to the device, it handled in a factory under a trusted environment before the device is leaving the factory to the field. So everything we build the trust under a trusted and controlled environment. And then we call it the root of trust of the entire system. And also, it is quite often for some security products, it contains multi-layer of software. So, for example, you may want to have a second bootloader because most of the time when the product is deployed in the field, we want to have secure firmware update or secure application update over time. So we need a second bootloader to handle this. In some case, some applications, we may also want to have an operating system that can help us in time scheduling. And we may also want to have many applications running on our product. So this becomes a multi-layer of software sitting on top of each other. So we can extend the concept of the code signing that Ray explained earlier here to ensure the authenticity of each layer of the software. As you can see from the screen, there's different layers like an onion. From the bottom, it is the core, the root of trust of the hardware. And then layer by layer, we can authenticate the different layer of the software. So the idea is to set the processor immutable bootloader as the root to authenticate the second layer of the software. In this case, it could be a second bootloader. And then from the second bootloader, we can authenticate the third layer of software. That could be a operating system and so on. So this is what we call the chain of trust. It is a multi-stage process of code authentication for the entire secure system.
Thanks, Stella. That was a great overview, and I love how you kind of walked us through with a visual. So I know that NXP, and again, we've been working with you for several years now and just continuing to develop our co-solution. You have a solution called EdgeLock Secure Enclave. And then also I've heard of Trust Zone. So maybe could you talk a little bit about the features that you have within the EdgeLock, and then sort of how is this different from Trust Zone depending on what the application is or the architectural design? So just for our listeners here, what are the differences and pros and cons of some of those?
Yeah, right, Ellen. Yeah, so on our newer products, we have the EdgeLock Secure Enclave built into our processor. So the Secure Enclave is a dedicated secure unit with its own CPU core and immutable memory and some other memory for handling all the security process. So these are the essential blocks that we use to build the root of trust of our processor. So the secure enclave, it protects the system on chip integrity and prevents application core from gaining direct access to sensitive data. So we mentioned earlier that the regulations it require the protection of the data and prevent any unauthorized access to the data. So in this way, the secure enclave can help us with protecting our sensitive data. In our case, it could be keys, it could be certificate, or any software IP that our customer they want to protect. And since the secure enclave is an individual unit, you can also offload your cryptographic operations from the application core to the secure enclave. So this is especially useful for some low latency applications and time-sensitive network applications. And the function of the secure enclave, it go beyond trust zone. So for some of you familiar with the trust zone, it is used to separate the secure and non-secure world by having a software partition on the same core. So it provides a logical isolation. When comparing with the secure enclave, as I mentioned, it is a dedicated secure unit which is individually operate independent of any other application core. So the secure enclave it provides the physical isolation comparing with the trust zone that use the logical isolation. So so it depends on the applications. Some OEM they prefer to use the trust zone for their project, and in any case, NXP processor we provide both solution for customer to choose the best solution for their applications and architectural design. So basically, the trust zone and also the secure enclave, these are the essential technologies that OEM should use to protect their product for the regulation compliance.
Awesome. Thank you, Stella. I really
Mhm.
appreciate you explaining that. Okay, another topic, post-quantum cryptography. So there's a lot of content out there talking about how post-quantum computers are going to be available at some point in the future, and they're going to be able to crack the algorithms that we currently have in our classical crypto and encryption. So specifically when it comes to RSA or ECC, which is the encryption algorithms that we are using today, we also know that those are likely going to be deprecated and not supported in the future. So Ray, I want to pull you into this a little bit. I know Keyfactor has a lot of expertise in the company as well as NXP about how we are helping our customers prepare for this PQC day when the computers will be able to, the computational power will be able to crack our current algorithms. So let's talk a little bit about why this matters to start thinking about now, what you see people doing, and sort of getting ready for PQC. I know it does vary by industry too. I feel like in the financial industry or maybe government, the people that are suppliers that are using products that go into government systems, perhaps are more ready to adopt or at least be ready for this. But can you just explain a little bit more about what you're seeing from your perspective on PQC readiness?
Yeah, I think people need to understand first off that PQC, post-quantum cryptography, doesn't need a post-quantum computer to calculate. The concept here is that what you're doing is taking algorithms that rely on these large prime numbers and replacing them with algorithms that are module lattice based, which is a segment of mathematics that is well beyond what I know, but we at Keyfactor and at NXP both have experts in understanding how that math works. So you don't need a post-quantum computer to do it, but these algorithms are quantum resistant because quantum computers can calculate prime numbers, big prime numbers, very, very quickly. That's why the older algorithms are just going to be outnumbered. So we've seen similar shifts in cryptography when SHA-1 was deprecated because normal computers could crack that as well. Therefore, what we're looking at is implementing new algorithms. Back to what Stella was saying, you have to implement those new algorithms in the secure ROM bootloader. So NXP has a line of computers, the IMX95 is an example, where they've implemented what's called MLDSA, which is a module lattice digital signature algorithm. That algorithm is designed in such a way that the key is of a specific size. You'll hear other keys, SLHDSA, or algorithms, SLHDSA. That algorithm actually, the key changes every single time you do an encryption operation. Therefore, the key keeps getting bigger and bigger. So what we're seeing inside of the IoT space is we can't have that. So what we're doing is implementing MLDSA. MLDSA is an algorithm that is already through the NIST standardization. Took many, many years in order to implement, and we've seen good adoption of it and a lot of technical information associated with it. So implementing those algorithms is important. What we're seeing in terms of customers starting to actually pick up and use post-quantum. Post-quantum itself, as Ellen pointed out, is really something that is in the best interest of, organizations and applications that are very critical. DoD, any defense, state actors, the governments, financial institutions, everything the financial institutions does is now computer-based. So implementing these kinds of algorithms is very, very important to them. However, the CRA, while it doesn't specifically call out, hey, you need a post-quantum algorithm, says, hey, by the way, when this happens, and it could be as soon as 2030, maybe 2035, you are going to have to be able to take devices and update them in the field. Some of this is possible through the use of hybrid certificates. Some of it is possible through the use of algorithms or, let me put it this way, hardware modules that can be modified, like TPMs, some secure elements. So what we're seeing is companies becoming more and more interested in, how am I going to do this? Because my design life cycle isn't a 1 or 2 year design life cycle. It's 5, 7 years. So in 5 years, we're at 2030. So you need to start thinking about this now and not thinking about this in the future. Thank you.
Exactly. At the beginning of the call, I wasn't sure if you were on it yet. I already thought it was 2026, so I'm just skipping years of time.
Don't, because
Okay, so
2027 is the CRA.
I know, that's exactly right. So, all right, so I want to shift a little bit into this last segment where we're going to talk about solution strategies. So I think we've set the stage pretty well in talking about why firmware signing and secure boot, again, because it is important as a manufacturer that you are going to be pushing patches, you're going to be pushing feature updates, you're going to be pushing new code out to your products, whether it's a surgical robot or whether it's a, some other system in a factory, and your customers, the operators, are relying on you to install firmware that you wrote, right? So at the most basic level, it's about protecting these operational environments that are then taking on new software by only validating the origin and the authenticity, and only installing software that you know where it's come from and what it's supposed to do. So I think, Ray, if you could describe a little bit, we like to try to, this is not a product pitch, but I do want you to explain a little bit about the Keyfactor sign server, because now we're going to shift into how Keyfactor plus NXP and talk a little bit about our actual integration. I'll pull up a slide in a little bit, but can you just describe that to us, and then Stella will go into some of the IA.MX architectures. So Ray, please go ahead.
Yeah, can you actually pull up that slide right now? Because I think it's important for us to say, okay, we've been talking about this esoteric signing and managing keys and all that other stuff. What does this look like in actual production? So how am I as a developer going to do this? So this is kind of the overview of how the two products work together and how signing works inside of the workflows that we have today. We all live in this CI/CD world, where you got an engineer using some kind of IDE that's writing things, let's assume for like a Yocto project build, where you're pulling some public repositories, you're creating applications. So you've got a meta custom layer or several meta custom layers that are put into a private repo. And then you actually go through the CI/CD pipeline where you're actually building the executable. So you build the image as an unsigned binary. The unsigned binary then needs to get signed. And if you look at the lower path, you'll see it's signed to go into production. So NXP has the SP SDK, which is their secure provisioning software development kit, which has a plugin which Keyfactor within the last 18 months has worked hand in hand with the team at NXP to integrate in with a signing product that we call Sign Server. Sign Server is the mechanism that actually integrates with that hardware security module, allows you to turn on and off signing operations, provides complete auditability, gives you so now I know when a HSM key is turned on, when the signing operation actually took place, who did it. And I can also limit the people who are allowed to sign by things like OAuth or mutual TLS. The sign server itself needs a PKI to work behind it. So in this case, we're showing Keyfactor's EJBCA, which is an enterprise Java Beans certificate authority. So it is an EJB. It also works with an HSM. And it one time will sign the signer key that is being used inside of sign server for signing operations. So the key that's inside of sign server is composed of a private key and a public key. A public key is something that you'll end up providing into the NXP SP SDK, and you can have up to 4. So you can migrate if you need to. So if one key got compromised, you could turn it off, and etc. The NXP Secure Provisioning SDK has a plugin that allows the APIs for sign server to sign payloads. So the SP SDK calculates the hash, submits the hash to sign server, performs the operations required to enable that AHAB boot, creating the signed binary. Signed binary can also be then loaded into the device inside of production using SP SDK as well. The other flow path that you see here is that signed binary can then be signed again by your OTA tool. So again, you go back to, what does the CRA require? Not only do you need to make sure that you're secure in production, but if you ever do find some kind of vulnerability, it's called a CVE, that vulnerability must be patched and made available to anyone who has your device. And the means to do this is typically through an over-the-air update. So you'll have to also sign the over-the-air update using that package. You can do that with sign server as well. So you basically set up a different signing key and a different what we call worker. And then you sign the OTA package. The OTA package is then delivered to the field device. The OTA agent that is on the field device verifies that the OTA package came from the right OTA. Then it knows it can use like the AB partitioning. It can burn it into the next partition, let's say the B partition, restart the device. Since the device binary was already signed, it also goes through the secure boot. This mechanism, where what you're doing is signing a binary that is executed through secure boot, and then a signed OTA package to make sure that you're downloading from a valid source, prevents any rollback attack or other attacks on devices in the field.
Seems
Okay,
there's some
not just my
issue with,
side.
yeah.
Ray, I think we lost you for a second there, so hopefully you can reconnect. I think he's pretty much wrapping up explaining this slide.
Mhm.
And now, Stella, I do want to pull you in. I know we have, Ray mentioned a couple times SDK. So let me click over
Yeah.
into this. Can you describe to us a little bit more about what this is and how NXP offers this to help customers implement Secure Boot?
Yeah, so before I go through these SPSDK, can I also add some notes to the
Please. Yes.
i.MX95
Yes.
device?
Go ahead.
Because
Go ahead.
Ray just mentioned about that. So we talked about the secure bootloader and secure enclave earlier, and Ray just explained how to use the SPSDK and also the sign server to sign the firmware. So actually, all these features on the hardware side, it can be enabled by our processor. So I take i.MX95 MPU as an example. It comes with the Ashrock Secure Enclave that I explained earlier. It supports the secure bootloader that in I mean in the past before the post quantum crypto becomes becomes a requirement. on some of the standard or regulation. We support the classical algorithm like ECC, and but now because of the PQC requirements is getting more and more important and more uh, uh, required by some of the standards and regulation. So we add the PQC algorithm to our secure bootloader. So i.mx95 is one of our products that support the hybrid boot mode. So the hybrid boot mode means that we support the classical one, like the ECC algorithm, and also we support the MLDSA, which is the PQC algorithm for the bootloader. So the reason for that is that for the hybrid boot mode, we need to provide a hybrid boot mode because we can provide an interim solution for our customer because it could happen that the MLDSA algorithm has failure, or it is possible for some applications they may still need to compile it with the current standard. So we provide the hybrid boot mode so that customer they can choose depends on their use case, their applications. They can choose either to use the classical algorithm for secure boot or the PQC algorithm for secure boot. So this is the reason why we include the hybrid boot mode in the i.mx95. And as Ray explained earlier with the diagram, we support Keyfactor's sign server solutions through our tools called SPSDK. So Ellen, now you may pull up that
I'm going to pull
slide.
that back up. And while I'm doing this,
Yeah.
Ray is traveling. He's at Embedded World North America in Anaheim. So if any of you are listening to this and then want to go speak with him, go find Keyfactor there. So just apologizing in advance for his hotel Wi-Fi. So
yeah, thank you. Sorry about that.
No worries. So Ray, we kind of wrapped up on there, and Stella talked about the IDA-MX95. Now I have asked her to do SPSDK, and then we're going to sort of wrap it up. We got about 5 minutes left. So Stella, please continue.
Yeah. So Ray explained a little bit from a high level how SPSDK and Keyfactor sign server interact. So let me explain a little bit more on the SPSDK. So SPSDK is our secure provisioning SDK, which it's an open source command line tools that our customer use it for generate secure image for the secure bootloader. We can use it for generating secret keys and also device certificates. It can be used for secure programming and provisioning and at production. So SPSDK is basically like a single tools that help our customer to enable security on our processors. And during the past 18 months, we work closely with Keyfactor to integrate the sign server API into SPSDK because, as I mentioned, SPSDK can be used for the production can be used for the secure provisioning and production. And with the SPSDK, developer they only need to deal with one single tool, which is SPSDK, and then they can link to the Keyfactor sign server API for signing their code image. And the good thing is with the SPSDK connecting to the Keyfactor sign server, basically customer, they don't need to have their own HSM infrastructure, especially for mass market customer. They may not have a secure room, secure protect factory that with the HSM equipped. So for this kind of customer, they could choose the Keyfactor sign server solution, and through SPSDK, customer can connect to Keyfactor sign server service and then sign their software. So yeah, so this is what SPSDK and the sign server operate.
Awesome. Thank you so much. I know 45 minutes is not a lot of time to try to cover these topics, but I do want to mention that we have a few resources that are attached here into the webinar. If you click onto the paper clip, you will find some links. Keyfactor has some content around CRA. We have an ebook. We've done a tech cast recently between NXP Keyfactor talking about this topic. And then there's also some NXP docs. These are just a few of the resources that we have. So take a look at those. Also, feel free to reach out to Stella, to Ray, or to myself to have further conversations, because we know that each of your use cases could be slightly different, and there's different ways that you can deploy this hardware and software combination depending on what your environment is, what your requirements are. So we're here to help consultants and figure out the best solutions. So just looking at the time, though, we are going to need to wrap up. I would like to hand it to you, Ray, first, and then Stella. Can you give one last piece of advice, sort of in summary, to the audience today? And Ray, please start with you.
Yeah, certainly. Thanks, Ellen. And sorry about the dropped internet. I think that it's very important for people to understand that the security of IoT devices is becoming more and more important. You're seeing takeovers of devices for denial of service attacks and other things. So people are using IoT devices as a means to get onto other networks and create bigger compromises inside of the entire domain. Therefore, we must remain vigilant. That's the concept behind all the regulations that are coming, and these regulations have been a little bit slow to be enacted. We need to, as developers of embedded systems, take this seriously and understand that it isn't just secure boot and all these other pieces of the puzzle that are important. We need to begin designing security into systems from the beginning of the design phase. Therefore, you have what I have termed DevSecOps, where your development, your security, and your operations are all working hand in hand in order to create holistic systems that can prevent attacks and prevent nefarious actors from using this new connected world in a means that's not very good for us. So thank you.
Exactly. Thank you, Ray. And Stella, one last piece of advice from you.
Yeah, so my advice is to plan ahead for security protection in your product design and run through a risk analysis for your applications. Because for compliance with the CRA, I think we first of all, we need to have a look on our applications, understand the use case, and run the risk analysis and create your own protection solution plan accordingly. So yeah, we highlight the secure bootloader, we highlight the code signing, and also secure update. So these are just a few pieces of essential components that you may need in your product. There's still some more other protections that you may need, depends on your applications. So yeah, having a risk analysis could help you to address all the risks that may have on your product. And also having a secure integrated solution for your product, and work with the strong ecosystem company that can help you saving your development and maintenance costs and time. Yeah. So
Awesome.
these are my advice. Yeah.
Thank you. I really appreciate it. Thank you, Stella. Thank you, Ray. Thank you to NXP for the great partnership that we have together, allowing you as a developer to leverage the NXP tool suite that you're naturally using, and then also implement Keyfactor's robust infrastructure for signing and signature verification with our PKI. So that's it. Really quick summary of the session. I appreciate it. Look forward to follow-ups, and thank you all for joining today. Have a great day.
Thank you. Have a great day.
Goodbye.
Thank you so much. Bye-bye.